Okay, so now let's do some statistical physics that involves some motion of the particles. So this is an equilibrium. It's instead of equilibrium, we actually have the particles moving. So one thing, just before I get into it, I wanted to mention, students have asked me about Brownian motion and diffusion and random walk. Like, what is going on? I have all of these things, and how do they fit together? So Brownian motion is basically when you just have particles that are sort of bumping around because there are other particles hitting it, right? This is just pollen grain that's bouncing around because all the water molecules are hitting it. Diffusion is basically the motion, right? You have some particles diffusing from one place to another place. Let's say we have a bunch of pollen grains, right? So if we have a bunch of pollen grains, we have some water over here, like this thing's filled with water, and we have a bunch of pollen grains, and they're all over here, and then they start moving to the right here. They start diffusing, and then random walk. Random walk is just a model that we use, right? So basically, it's like you have a particle that can take a step to the left, or it can take a step to the left or the right, and then it keeps maybe it takes a step that way, and then takes another step that way, and then decides to take a step back, and then a step back, and it's random which way it goes, but it's basically going left to right, based on just random step size, this little delta here, and for each step is done at some period of time tau. So it takes a step at tau, like maybe tau is a second, so it takes a step at 1 second, then it takes a step at 2 seconds, and each of those steps is this length of this little delta there, like that. So that's a different delta than our triangle-y delta, but that's also called delta. Since it's a random walk, since we randomly go left to right with equal probability, the average distance that you would get if you looked at a bunch of particles, right? You say took a bunch of particles and you put them all in one spot, right? So start them all here and let them all go left and right. So some will go left, right, left. Some will go right. So they're all going to go. So all of these are going to spread out over a period of time, and your particles that were in one spot now are spread out into a mess that I've created here. But the average x distance, they all started right here, and they're going to be an equal number on the right, and there's going to be an equal number on the left, and so the average x is going to be 0. Now, now what we can do is not let the left side and right side, those negative signs on the left cancel the positive signs on the right. Rather, what we'll do is we'll square the distances of each of them, right? So we'll take, if there's a particle over here, we're just going to look at this as our x for that one. What we're going to do is we're going to look at here, we're going to look at our x squared, and for every particle, let's look at our x squared, and then find the average of all of those x squareds, and you'll find that that's going to be equal to the number of particles that you have times the number of steps that you take. Sorry, not the number of particles. The number of steps you take times the distance squared. So the big equation for diffusion is this equation here. So, and I should say that it makes sense that our x squared will go up as the number of steps, not the number of particles. Because the number of steps basically means, if you wait a longer period of time, the thing is going to take more steps, and this thing will spread out further. So our average x will be bigger if you allow it to take more steps over a longer period of time here. The really important equation is our average x squared is equal to 2 diffusion constant times time. And so we can relate our d, our diffusion constant, in this equation here to our random walk using this equation, or if we have just some sphere, and you did this in the lab, you can actually connect a sphere. So this is for our friction coefficient for a sphere, and so we can actually calculate our d for that sphere using this equation here. So what we want to get in the end is basically, compare our x squared, or our root mean x squared, which is the square root of the left hand side here, using 2 dt, but you can, d can be related to the random walk, or it can be related to the actual particles down here. So basically the situation that you want to think about here is, it depends on your basically your situation, right? So like basically if you have a long narrow tube, and what I mean about situation is like it depends on your how many dimensions you have. So right, so this is our so what I have written right here that I keep boxing over and over again is basically for 1D random walk. And so that's if you say you have a long narrow tube and you have a bunch of particles in it. And so you can figure out what the average x is over some average x squared over some period of time, by using a 1D random walk. So if we have a long tube, we use a 1D random walk. If we have, say, there's some little pancakey thing, and we want to know how long does it take to get something to the edge of this pancake, a distance like r away, then we'll have, we'll use our x squared is equal to 4 dt, because this one is two-dimensional. And then if we have, say, some particle, and we want to know, like we have perfume, a bunch of particles of perfume, we want to know how long does it take them to get to, the edges of this spherical room, like how long does it take to get to there, distance r away. We can do delta x squared is equal to 6 dt, and that's because this is a 3D situation. And the r that you'll want to use is basically you'll equate this thing to r squared. You're essentially saying that r is equal to x RMS, which is equal to the square root of the average x squared. And so these are the different situations, and I think in your homework 10 you had a problem involving a neuron and a bunch of particles, and in this narrow tube, and so you do 1D random walk. You also saw one with a disk, and then you've also I think we've also looked at some 3D examples. Okay, so now let's talk a little bit about diffusion. So here we have, this is, Fick's first law. And so for Fick's first law, the situation that you want to think about is, so let's, let me, actually no, this is good. Let's imagine you have, let's say you have a concentration. So here we have like a concentration of oxygen, and this is, let's say this is in your lungs. So here's like, so this is basically where the membrane is in your lungs, and this is where the alveoli, and then this is over here is where your bloodstream is over there. So basically at the alveoli, you have oxygen that is basically kept fixed. So the O2 levels are kept fixed over here. You just keep bringing oxygen into your lungs, and in your bloodstream you have a relatively low level right inside the membrane, and the blood basically keeps that really low because the oxygen keeps moving out into the bloodstream, so the O2 keeps moving outward, and oxygen keeps moving inward like this. So my point is basically that this point is going to stay right here, and this point is going to stay right here, and we're just going to look at this constant slope. And so basically what Fick's first law says is that if you look at the concentration and look at the slope of the concentration, dc over dx over that membrane, you look at that slope, and okay, we have some positive slope here, and then we say negative, the diffusion constant, times that slope, so that would be negative means, now in this way, then this is the direction of our flux. So Jx is going to be negative because we have a positive slope of concentration over distance. So I know usually we've just, when we talk about this, we just have a straight line. We just have some some straight line. And this is like our x and our concentration up here. And I just wanted to give you a real world example where I have the alveoli where it stays fixed concentration there, and down here we have the concentration is fixed down at 0 in the bloodstream, just to give you a real world example there. And then we have this is fix the second law. And so the one just real important thing here to know is that this is concavity. So basically we look at the sign of the concavity, right? So this is like if it's concave up, it's positive, and it's concave down, it's negative, and that tells you how the concentration will change, right? So one example would be, let's say you have a concentration, you drop a bunch of perfume in a stream of water, or like a little trough of water or something, and then at some period of time you have like a bunch of particles right here and then fewer further out because they're starting to diffuse away. And so the way that you would draw this concentration as a function of position is you draw it like this, because there's a bunch in the middle and then fewer further out. And so this equation basically tells you, for example, we could look right here and we could say, okay, so right here we have a negative concavity, right? So this is negative concavity. So that means that the concentration, right? So that means that this right here, this concavity is negative, so that means the concentration with respect to time at that point is going to decrease, so that we know the concentration will decrease right here. On the other hand, right over here, right, this looks like we have, positive concavity, right? And so positive concavity means that this is positive, and so that the change in the concentration over time right here is going to go up, right? Same with over here, we have a positive concavity at this point, so this is going to go up. So, just a little bit later, and then if you looked at, a place like here and right here, these inflection points, it's actually not going to, there isn't any concavity, so that won't change. So basically, a little bit later, we're going to have this look something like, something like that. I'm sorry, I should have, the bump should be, let me go back, do that right. So we got a little bump right there, and then it goes down, right? So it's basically going through these points. This has gone up, then in the middle here it's gone down from where it was, and then back over here it's gone up a little bit.